Okay. So, hello. Well, I will skip the introduction. So I will just give a talk about the different development that Omega team has done since a long time on calorimetry. So as a first reminder, I would say that years ago, calorimetry was basically just was not as much requiring things as now. So at first, we were requested the eta, phi, and the energy. And then later, people requested a complete position. And recently, also, the time has also been included in the requirement of calorimeters. However, all of these measurements don't have the same impact depending on the detector that you plan to use. So in all cases, high granularity means a lot of channels. So you have to be very low power. This is true for all the detector, but some detectors have advantages versus some others. For example, for the ILC, we can use the power pulsing technique, which is not the case, for example, for the CMS HGCal. So for the high luminosity calorimeters foreseen at CERN, we will have to use low power electronics and some cooling system in order to have a reasonable temperature increase. So in both cases, we need to have a very large dynamic range. So from this means the MIP sensitivity with low noise up to lots of charge. The timing, depending on the detector, is needed or not. So this is crucial for the HGCal in order to avoid the pileup and determine the tracks of the particle. Whereas for ILC, it's not mandatory for the ECAL, and it's few nanoseconds are requested for the HCAL. In both cases, as you have a lot of channel, we need to have the electronic embedded inside the detector, and the main challenge is to send the data out. So there are different schemes. So we have a daisy chain and low power buses for the ILC detector, whereas we need to have high speed links for the high luminosity calorimeters. Same difference also concerning the radiation level, as pointed out by Dave. The radiation level is clearly doubting at the high luminosity LHC, whereas we don't really care on the ILC. So concerning the history, we started to work on the calorimeters for the ILC, and just to give a number, depending on the technology which might be chosen, we will have up to 100 millions of channel or 70 millions of channel for the ECAL and HCAL, which is really a lot if you consider the energy, the heat which is induced by every channel. So we started to work within the Callier collaboration, and we did a lot of R&D in order to provide chips for these different calorimeters. So one of the main requirements is, well, it's required to have the particle flow algorithm in order to really reconstruct the tracks of all of these particles. So the requirement for the electronics itself are, I already told them, so low noise, low power, highly integrated, large dynamic range, and also zero suppress. For some, we also need to have, we benefit from the power pulsing. And for all of these chips which were developed for the ILC, we have some common readout features. Well, this command readout feature, I will not really give too much detail. The chip are auto-trigger. They have analog storage and except for the HDH card, they have also digitization. They are read out by a token ring system, which means that every chip is read one by one. And they have a common DAQ. If you have a DAQ for hard rock, you can read out Skyrock or Spirock. Because we benefit from the bunch of the ILC, which has during 1 millisecond some event, and then for 199 milliseconds there is nothing. So there has been few updates on the third generation of chips for ILC. So we have a really independent channel feature. We have also I2C links for configuring the chips, which is saving a lot of time when you have to configure your complete calorimeter. And we also embedded a PLL inside the chip, which means that you don't need to provide different clocks to your ASIC. You just need to provide this 5 or 3 or 2 megahertz clock, which is the clock of the machine. And the chip internally generates a higher frequency, which is used for the digitization and the digital part. So I start with the Skyrock chips, which is intended to read out this silicon pin diode. This chip has been designed in AMS 0.35 micrometer technology, meaning that we have a dynamic range for the power supply of 3.3 volts. It has an auto-trigger capability up to half a MIP, which is quite small because it's 2 femtocoulomb. There is a large dynamic range, and we have an analog memory which sample the interesting event, which are sampled only when a trigger occurs. The power pulsing, using the power pulsing at 1% rate, duty cycle, thank you. We reach 27 microwatt per channel. So basically, the analog front end is made of a charge preamplifier, where you can tune the gain by changing the capacitance, which is followed by a fast line, so a fast shaper, which is compared to a selectable threshold, and which gives you a trigger. And you have 2 slow channels with different gain, 10 and 1, which give you a charge information. So the trigger is delayed, and in order to sample the maximum of the waveform, and this is stored in the analog memory. There is also, but it was not foreseen, it was not used up to now on the ECAL. There is also a TDC. So afterwards, this is digitized by the embedded ADC. So few results. So using the nominal gain requested for the ILC, this is here what we call the S curve. This is a trigger efficiency. So this means that you inject the equivalent of 1 MIP in all of the channel one by one, and here is the result. So you can see that you are able to set your threshold here, and your chip will never trigger due to the noise, but always trigger due to the MIP. So this is for another gain. This is a gain which is currently used which was currently used in BEAM. Concerning the linearity, I told you that we need to have a very large dynamic range. So as you can see on the low gain path, we are linear up to 2,000 MIPS. And still, it doesn't prevent us from being able to separate 1 MIP to the next MIP with this weaker gain. So I told you that we benefit from the power pulsing. So what we do in this chip, we are not switching off the power supply. We are just switching off the bias. And so during the acquisition, just a part of the ASIC is active. And later we have the digitization, which is using less power. And during the readout, which is sequential from one chip to the other, we are even using less. So one slide that I've taken from Vincent's talk concerning the detector itself. So well, the measured signal-to-noise ratio in beam was 18 for the charge measurement. And this test beam campaign was using this front-end board. So these are BGA, there are 16 BGA Skyrock 2 chips. So you have a stack up of up to 10 front-end board. This naked chip directly embedded in the PCB is the other option foreseen for the ECAL. Well, this is just a nice plot from the beam. Well, concerning the system, when we move from one chip to a 100 million channel system, we face new issue. So, for example, noise, crosstalk. So you can see here, so some what we call square event, or here this is for another detector. You have this kind of monster event. And all of this kind of issue, retriggering and digital noise, they occur only when you go to a large system. So there are many things that you need to check and to completely manage in order to avoid this kind of thing. So now I switch to the chip which was designed in order to read out SIPM. So this chip is PROC. So this was done in collaboration with DESI people because they are using this SIPM. So the requirements are more or less the same as Skyrock. I mean, large dynamic range, low power. They have a higher another constraint which was not foreseen in the Skyrock. They want to measure the time, and it's not a problem. They want to measure the time. So and they also need to have an input DAC which will compensate the gain variation of the SIPM. So the front end is more or less very similar to the one from Skyrock. So here we have a voltage. We have two voltage preamplifier with two different gain. We have this input DAC which is able to tune the high voltage on the SIPM itself. So this is used to compensate the temperature fluctuation of the detector. We have also a fast channel which gives a trigger which samples the two slow channel charge, and this is read out later. This is digitized and read out later by the ADC. So I like to show this slide because almost nobody understands anything. Just to show you that these chips are really system on chips, and it's a very complex digital part which is managing all of this, all of the different part of the ASIC. So this was just to scare you a little bit, but the good thing is it's working. Sorry? Okay. So some measurements on the Spiroc chips. So I can show you that we are able to see the single photoelectron separation, and so this plot where I have made this measurement, but this is not pure only measurements provided by me. So here you have, for example, measurements done by DESI people. I don't remember if this one was using power pulsing, but I have some plots where they are using power pulsing. And so the funny thing is when you are injecting every time at the same at the same position. You can even see the time walk from one photoelectron to two photoelectrons on the time measurement. Concerning the linearity of the chip, so the setting was not set to the nominal one foreseen for the ILC. So this is why on the low gain here, you would say, hey, we don't reach a 2,000 photoelectron dynamic range where it's supposed to be linear. Yes, this is true, because this is not the, I mean, this is not the nominal gain. This plot is interesting because this plot was done by DESI people, and they have been using internal trigger in red and external trigger, and they succeed to reconstruct, I mean, the same single photoelectra using our chip. Here, on this plot, they play with the temperature, and they used the input DAC in order to tune the gain. And as you can see, the peaks are always at the same position. So, I mean, they are quite happy with the chip concerning that. They also study they also start to study the power pulsing, because in order to have a very large detector, I mean, this is something that you need to be interested in. Sorry. So I think I don't have that much time. So I will just show. Well, you have seen already this picture in many presentations today. So here is, for example, one of the results that they have in beam. And the last chip which was designed for this ILD detector is Hard Rock, which was developed for the HDH-Cal. And the front end looks similar, so just the architecture is different. But so we have a variable gain preamplifier, which is followed by 3 fast shaper, which have different gain and which address different dynamic range. So, and you compare this shaper to 3 threshold, and thanks to that, you have an information, or you have the information if there was a charge in this channel, and if yes, was it a weak, an average, or a big charge which was deposited in this channel. So. Few analog measurements, just to show that it's linear on the requested dynamic range. So for the weakest gain, we are linear up to 300 femtocoulomb. For the middle range, we are up to 10 picocoulomb. And this is for Hard Rock 3. This measurement is for Hard Rock 3, because it was up to 15 in Hard Rock 2. How much do I? 10. Okay. Well, I will skip some. Well, this is not interesting. So yeah. So this is well, you have seen that already today. Yes, there was also a version for micromegas, which was developed with ANSI people, and they have a very good noise performance, because they could set a threshold as low as 1 femtocoulomb. So then I move to what is most interesting for you here is CMS, the CMS development. So thank you, Dave, for your slide. So the requirements for the CMS are really low power, low noise. The new thing for us is this very high radiation leaven. And also a faster shaping time with a continuous data sampling, digitization, and readout. Because in CMF, there is no dead time, so we cannot benefit from dead time to digitize and then readout. So we have designed 4 ASICs since 2 years. So we first started with a test beam-oriented chip, which was still submitted in this AMS technology, and which was made for test beam. So there is still this acquisition phase and then readout phase, and later. We have submitted in TSMC 160 nanometer technology three other chips in order to go toward the final version of the chip. So one of the main drawbacks is that the analog power supply available is only 1.5 volt for the front end. So this is limiting the dynamic range of the preamplifier. So, well, this Skyrock 2 CMS is just, it's just a rolling memory. So consider that you have more or less the same front end as the Skyrock 2. You have a charge preamplifier or a current preamplifier, because this is tunable by slow control, which can read out both polarity, because at CMS they don't know if they will use a positive or negative signal. Well, they know right now, but it was not the case 2 years ago. And this chip has a 40 megahertz circular memory. So this means that you sample the waveform every 25 nanoseconds and store that in an analog memory. So this chip is currently used in test beam. So here, for example, is a sample of what you see from the chip and from the scope. So I skip. These are the results for the measurements. So I will skip a little bit. So concerning the noise, it's something very important. We have estimated the parasitic capacitance of as low as 34 picofarad. So it's not enough. It's less that we will have on the HG-Cal. So this is the second configuration. One very important thing concerning this HG-Cal feature is instead of using a low gain channel, we plan to have to use time over threshold technique, because this event will be very rare. And so what will be done is we will compare the preamplifier with a threshold, and thanks to that we have an information concerning the charge deposited on the preamplifier. Something which is important at the system level is the coherent noise. At first, especially on the front-end board, there was not enough, it's basic, but there was not enough decoupling capacitance, and the coherent noise was just completely crazy on the front-end boards. Well, it has been solved since. Concerning the time measurements, for tenths of MIP, we plan to have a very good precision, tenths of picosecond. So this is something that cannot be achieved with very low charge injected. Well, we also, I'm sorry, I have too many things to say. We also have tested the the Skyrock 2 CMS with MPPC, with DESI people, and here is the results that we obtained. I will skip the result from test beam because you have seen that in Dave's slides. To focus on what will be the HG-Cal readout ASIC. So we will have a preamplifier followed by a shaper. We will measure the time of arrival. We will measure the time of a threshold. So this is not connected here, but here. We will have a lot of digital part which will manage all of this signal coming from the TDC, the TOT, and the ADC, because they don't. They will not. The result will not be known at the same time. So we need to align everything. So the digital part of this chip will have a lot of things to do, because so there is this aligning things. There is a level 1 buffer with local zero suppress. This will be controlled by external command. We need to make a linearization of the charge measurement. We can then apply a gain correction, and also we need we need to provide a
Less than 5.
okay. We need to provide also trigger information. Trigger information is given by merging 4 or 9 cells together in order to measure the total energy deposited in these channels. So this chip was done in collaboration with CERN, CEA, and Imperial College. And up to now, the version that we have in hands, only this part which are not grayed were embedded inside. So I have, this I skip. So here is the architecture of the front end. So we have a preamplifier which is followed by a differential Salon K shaper, which will be continuously digitized by a SAR ADC. There is one TDC who measures the time of arrival, and we have 2 TDC which are measuring the TOT. This is still the results are still brand new because we had a lot of trouble with the test board that we received at the beginning of this year, of February this year. So I can show you only few results. So here is the waveform of what we can see on the board that we have, and I would rather focus that the most important thing is we check the linearity and also the time walk and the noise. Well, the linearity is okay. The time walk is fine. Concerning the noise, well, we are not really happy with what we have measured right now. We have a lot of digital noise when we make the complete chain working. I mean, the ADC and the front end and the back end working together. Concerning this, the back end of this chip, so I told you there is an ADC, which it's over. Okay, it's over. So there is an ADC, a TDC. Yeah, for the readout, we will have 2. Whoa. Well, the data will go out at 320 megahertz, okay. And the trend, yeah. Then concerning the timing, I will just show this this slide because some people talked about it. I mean, we cannot have for 1 MIP, depending on the detector, we cannot achieve a very precise measurement. Well, that's all. Oh yes, this is my summary. You will read. Sorry.
So questions. We have been flooded by information, so we'll be a bit difficult. But there is one piece of information that I missed. Actually,
yeah.
Number of information that I missed. But at least I have to ask you.
Yeah.
I mean, in the last chip that you have been presenting, what is the power consumption that you have?
So the target is it's 5. It's 5. It's not written. It's 5 milliwatts per channel.
5 milliwatt per channel. No.
Yeah. Oh, it's not 5. Oh. Oh, I think I have it on the backup. It should be written somewhere. No. I'm unless I removed it.
You're also getting.
Oh, yeah. Okay, yeah.
95. Slide 95.
No. This is just a.
These are the numbers. So I mean, I'm interested in using some of these chips, but that is to say, I mean, now I'm puzzled because the power consumption that you mentioned for the Spirock and for the Skyrock is when you go power first.
Yes, sure. Yeah.
No, this is the second part of the question. So now, if you don't do power pulsing, is 1 milliwatt
No. Really? Because for the Skyrock and Spirock is not it's more I would say 5 or 6 milliwatt per channel. Yeah. But you have still dead time.
So do you understand correctly that in the last chip that you described, you also had a way to correct for the gain because you're using just one gain, one ADC. You had only one ADC, and you were correcting using as a time of a threshold, right?
rather than 2 gains?
Yeah, if you go there is that linearization stage, right? There you are correcting the fact that you have some saturation
Well,
by
principle, the TOT is not linear.
Mm-hmm.
And yeah.
Okay.
And when we will switch from the ADC charge, from the ADC measurement to the time over threshold measurement, there is a very large. I consider that there is a large gap.
Yes.
I don't know. I don't exactly know how this will be done.
But let me get to the question.
Yeah.
The question is. Is that stage sufficiently flexible so that, for instance, if you have input from silicon PMs, you could correct also for some saturation effects in the high range?
I'm sorry, I forgot to say about something. This TOT technique is absolutely not working for the silicon PM.
Ah, okay, great.
So,
So we got the answer.
So we will have to use. We won't use the TOT for the SIPM.
Okay. So for the
Time we know it's not our
okay.